Hey, you guys. I am so sorry again for all of my technology struggles this morning. I still don't know what happened, but I do know that we did not get to finish our discussion on sort of the history of our different models of what an atom looks like. And I just want to make sure that you guys all feel good about sort of the progression of that atomic model, and especially with how Rutherford's gold foil experiment contributed to our understanding of the structure of an atom. So we'll start at the beginning and go especially through Rutherford, and then briefly touch on how our understanding has developed since Rutherford. But we're going to start with Dalton. And so remember, Dalton had this idea that all matter consists of these tiny particles that are indivisible and that have the same properties as the matter itself. So we were talking about how like coffee atoms would maybe smell really good and be the smallest piece of coffee that you could possibly get, and maybe these coffee atoms would be brown like coffee beans, stuff like that. But the important thing here is that Dalton was considering these atoms to be these hard little balls that you couldn't break down any further. They're sort of like the smallest, they're the last level. They're the smallest things you can have, indivisible. And so they can't be taken apart. And so from there, we are going to bring in J.J. Thomson and his cathode ray experiments. And so J.J. Thomson was the one who figured out the plum pudding model. So if that name is your favorite, it's definitely my favorite. That's where he's coming in. And with his cathode ray experiments, he was basically he was setting up these two electrodes inside of the cathode ray, and then applying a voltage across those electrodes, and that is going to cause this beam of particles to flow from the positively charged, or from the negatively charged end to the positively charged end. And he did a bunch of stuff with magnets and different charged plates, but at the end, what he had discovered is that there exist these tiny negatively charged particles that are way smaller than the size of an atom. So we have these tiny little pieces, and they so like with that knowledge, an atom can't be indivisible, because if we have these tiny little particles that are way smaller than an atom that have this negative charge, they have to be coming from somewhere. They have to be coming from an atom. So J.J. Thomson suggested that an atom is not the smallest thing that we can have. An atom can actually be broken up into different kinds of pieces. So he had discovered these negatively charged electrons. So I'm drawing some electrons here. But he also knew that atoms as a whole were neutral. They didn't have a charge. So if we have these negative charges, they need to be balanced out by something else um, that's positively charged, and that would bring the whole charge of the atom back to a neutral state. So he suggested that these negatively charged atoms exist within a sort of sea of positivity. So this this blue stuff is supposed to represent this sea of positivity that is housing these negatively charged atoms, or these negatively charged electrons. So the idea is sort of like if you think of like a blueberry muffin. If you were to open a blueberry muffin, you would see on the inside of the muffin all of these blueberries, right? And the blueberries in this case would be the negatively charged electrons, but they're sort of studded or embedded within this dough. And the dough would be this positive charge that's just sort of is flowing around the negatively charged electrons. So on the whole, the atoms are going to be neutral, but within each atom, there are these negative particles called electrons, and a soup of positivity surrounding them. So that brings us to Rutherford and his gold foil experiments. And just so that we're all feeling good about the setup for what he was doing, um, this gold foil is really similar to like aluminum foil that you might have in your kitchen, except it's super thin. So it's actually just a few atoms in width. So if we're looking at the gold foil from the top, we could imagine that it might look something. These are overlapping a little bit more than I meant. them to, but it might look something like this. So if you imagine looking down at a piece of aluminum foil, like from the edge, so like looking at the thin edge of it, um, except if that aluminum foil was gold, maybe it might look like this, where it's just a couple atoms in width, and that's what we're shooting our particles at. So remember that Rutherford was firing these particles called alpha particles at this gold foil. So the alpha particles had a positive charge, so they were positively charged, and they were also pretty big. So that'll come into play later. But what he was doing was he was firing these alpha particles at the gold foil, and then he was seeing where are the alpha particles landing? Are they going straight through the foil or what? So he had this screen, this detector screen that would light up every time an alpha particle hit it. So if the alpha particle was to go straight through, the screen would light up right behind the gold foil. So we would get light up areas right behind. If the alpha particle was to be deflected, then we might see a beam that, or sorry, we might see a light up in this sort of area, or if it was deflected down in this way, maybe the screen would light up back here. And if the alpha particle was to be totally reflected, like if it was going to be bounced back in the opposite direction, then maybe we would see that the screen would light up somewhere like right here, or maybe if we shot it and it came back this, we'd get a region that would light up over here. So Rutherford was actually imagining that since he was firing these like semi-heavy alpha particles into these atoms of gold foil, they would actually go straight through. And this isn't necessarily an intuitive like assumption. I feel like if I'm imagining us shooting particles at gold foil, like of course the gold foil is going to stop the particles. But the idea was that in this plum pudding model, in J.J. Thomson's model, all of the positive charge of the atom was spread throughout the entirety of the volume of the atom. So like even though there's this positive charge, this soup, it's so diffuse, it's so spread out that it's not going to affect our positively charged alpha particle. So even though we're shooting this positive particle into a sea of positivity, the positivity in the atom is so little that it's just like not even going to affect this alpha particle itself. So J.J. Thomson was expecting all of the alpha particles to just go straight through. But what he found was that instead of going straight through, a small number of the particles were actually deflected. So he was getting the screen lighting up in these other regions that are suggesting that the particles aren't going straight through, and a couple even bounced back and were reflected towards the back side of this deflecting, or towards the back end of this detecting screen. And so he was really, really surprised by these results. He said, what did he say? Here it is. He said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you'd fired a 15-inch shell at a piece of tissue paper and it came back and hit you." That's how surprised he was by this. So based on these results, we can't, like, it's not compatible with this idea of this diffuse sea of positivity, because what in a diffuse sea would be causing these particles to bounce back? It's not strong enough. This reflection is actually more compatible with Dalton's idea of these like billiard ball like atoms, right? So what Rutherford concluded was that we actually have to have these small um, dense regions of positivity in the middle of atoms. And these small dense regions of positivity, what we are calling the nucleus, are what's causing the weird behavior of these alpha particles. So he's saying all of the positive charge, instead of being spread throughout the whole atom, is concentrated into this one dense small area. And so this explains the behavior of the alpha particles, because if they're not getting near the nucleus, they're going to go straight through. If they do start to come close to the nucleus, they might be deflected. So in the same way that two sides of the same magnet are repelled by one another, these positively charged alpha particles, and the positive charge in the nucleus, they're going to repel, and so the beam might get deflected in that way. And if the alpha particle was to hit the nucleus straight on, it might actually be totally bounced backwards. So all of the charge in the atom, all the positive charge in the atom, coming right in the middle um, in a very dense area, most of the mass of the atom, all the positive charge of the atom in that nucleus. And then he still was thinking of the electrons as being sort of like just floating around the outside of the atom. In Rutherford's model, most of the atom is empty space. So all of the yellow area highlighted here, that's empty because all of the mass of the atom is in the nucleus, and then the electrons are so small they like barely even count. So most most likely, if you were to shoot an alpha particle through an atom, it would be hitting empty space and going straight through. Okay, so after that, sorry, what am I trying to move here? Um, so after Rutherford's model, we went a little further in our description of what an atom looks like, and Niels Bohr came in, and his thought was that instead of being just sort of scattered about the nucleus, electrons are going to exist within distinct shells and orbit the nucleus in the same way that planets orbit the sun. So there's just going to be little sort of like rings around the nucleus, and around these rings in an orbit, the electrons are existing. Um, and then later, we had even more development. So people actually discovered that neutrons also exist in the nucleus. So there's positively charged protons and neutrons. And then people like Heisenberg and Schrodinger found that instead of existing within discrete orbitals, electrons are also, you maybe have to think of them more like waves rather than particles, and they're sort of like buzzing around the nucleus in these clouds rather than in distinct rings or distinct orbitals. So now we don't think of electrons as existing in these rings, but rather in these clouds. Um, so I hope that this video clears up any confusion that you might have had that was left over from this morning. Um, and yes, I hope it's helpful, and I hope that you all are feeling good about the history of our different models of the atoms.